Okay, last video on chapter 9, osmosis. I love to start out my talk on osmosis with this picture because, growing up we all were taught that you could learn things by sleeping on your books if you needed to cram the night before test. And, it never did work, right? So, that's why this is funny, because I wish it did. I totally wish osmosis worked this way. I was the type of college student, I would study late at night. Anybody? You wait until 10 p.m. to start the assignment or to start your homework, and that would never go well. That's why I'm so dependent on coffee, unfortunately. So I wish osmosis worked this way because I would have rather got a lot more sleep through college, but it didn't work out. So here we are. What is osmosis? It is the passage of, here's a key word, solvent, through a semi-permeable membrane separating two solutions of different concentrations. Everybody tends to think it is the movement of particles. We don't think about solvent moving. We always think about particles and ions and molecules moving. So get that out of your head, because this is totally different. And I guarantee I'm going to have some people on the exam tell me that it is the movement of solute or particles. It is not. It's the movement of the water or the solvent. Semi-permeable, meaning stuff can pass through it. Maybe large things can't, but small things can. Definitely solvent size molecules can pass through. And the whole point here is that you have different concentrations, which means you have a gradient. Okay, when you have different concentrations on either side of a membrane, you have a gradient. And how does solvent move? You need to think about, does it move from an area of high concentration to low or low to high? And for osmosis, it is always going to move from an area of low concentration towards an area of high concentration. Because remember, we cannot move the particles, we can only move the solvent. And so it's going to try to always dilute the side that is more concentrated. Keep that in mind when you're looking at these figures down here. Osmosis depends, here's another important statement, on the concentration of particles. We don't care about what the particle is. All right, so everything I just taught you to think about with ions and electrolytes, this is different. Okay, we don't care if it's a +2 or a +1 ion or what it is. We just call it particles from now on. They're all particles. Okay, we don't care about the identity as much as we care about the concentration. So now that we've talked all around osmolarity, what is it? It is the moles of particles per liter. Anybody watch SpongeBob growing up? I feel like SpongeBob could get behind osmolarity. Remember was it Barnacle? I honestly didn't watch SpongeBob growing up. Was it Barnacle Boy or something? I feel like we could have a character called Osmolarity on SpongeBob and call it Particle Boy. If it doesn't tell you how late it is, that just did. Okay, sorry. Let's get back on track here. And looking at these two figures, actually, what does this say right above it? 1 molar NaCl would be, okay, so for example, if we're going to break this down, how do we apply osmolarity to compounds and things like that? If we had 1 molar NaCl, remember that this M stands for moles per liter, right? Moles per liter. So if we have 1 molar NaCl, we have 2 osmoles. How did we get that? Well, because we have 1 mole of sodium particles, and we also have 1 mole of chloride particles. Remember, we don't care that it's sodium and chlorine anymore. We just call them particles. So we have 2 moles of particles. That's why it's 2 osmoles per liter. Okay, what about glucose? If we have 1 molar glucose, remember this is moles. We have 1 mole of glucose particles per liter. So we have 1 osmole. Why? Because glucose is just, we're going to have from the glucose just 1 mole of capital G glucose particles. Glucose doesn't break apart into anything the way sodium chloride does. So you need to know if a compound is going to break apart into ions or not, and how many ions you would get, but you don't care about the identity of them. You just need to know how many. And that's going to tell you how many osmoles you would get. All right, we'll do more practice on that later. But looking at this figure here, we have a semi-permeable membrane in the middle. This is the black line separating two sides, two solutions, different concentration. On the left side, we have something with higher concentration. And on the right side, we have something with lower concentration. So remember, solvent, earlier up here we said, flows from an area of, so the gradient, the way it's going to flow is from low to high. And that is concentration. Low concentration to high concentration. So if I ask you which way is solvent going to move to try to make the osmolarity equal, it would move this direction, across the membrane this way. The solvent would. Okay? And what would it look like when it got done? Well, if the solvent is water here, which is what it looks like, you would have a picture like this now. A lot of the water would move, so you'd have a lower volume on the right side, higher volume on the left side, but now you'd have equal concentrations per liter. They're both 2 osmoles. And these solutions, because they're the same osmolarity, we call them isotonic. All right, isotonic. These solutions are isotonic, means they have the same osmolarity, same number of particles per liter. Well, scratch the poll question, although we would have had a good one. Okay, that also leads to, did I get to it down here? I guess not. I also need to introduce 2 other terms. Okay, because if we have isotonic, meaning same osmolarity, we also have something called hypotonic, meaning lower, hypo, meaning lower osmolarity, and hypertonic, meaning higher. That is talking about a solution that has higher osmolarity. If it has a lower osmolarity, it has a lower number of particles per liter of solution. If it has higher osmolarity, if it's hypertonic, it has a higher number of particles, be it ions, be it glucose, be it insulin, be it proteins, per liter of solution. Okay? All right, a little practice on this just to kind of review. Here is my best tip for you. When calculating osmolarity, ask yourself how many particles, how many ions, or, it's not always ions here. It could be molecules. In the case of glucose. Will this compound produce when dissolved in solution? So, and that will help you calculate osmolarity. So if we have 0.5 molar KCl, potassium chloride, what is the osmolarity? So we're trying to calculate how many particles per liter. So we know we have, essentially I'm going to rewrite this. We have 0.5 moles per liter of KCl. Well, if we have that, then we know this is going to break apart. KCl will break apart into K+, and it'll dissolve into 2 ions. So we're going to have 0.5 moles of potassium ions per liter, plus we'll have 0.5 moles per liter of the chloride ions. And these are just particles. I should write particles in, but I'm not going to erase. So all you do is you add these 2 together, so we will have 1 osmole. Or you could say it has an osmolarity of 1, okay? 1 osmole. The osmolarity equals 1. Because we did 0.5 plus 0.5 moles, which means we have 1 mole per liter, and that is an osmolarity of 1. All right, number 2, if we have 1 molar calcium chloride, that means we have 1 mole per liter of CaCl2. And we know this is going to break apart into one calcium cation, that is a 2+ charge, and we would get 2 chloride anions. I'm looking at the subscript here to tell me how many of those we would get. So that's going to be equal to 1 mole of calcium, I'm going to write particles to drive the point home, per liter. Because you actually don't care what the charge is here. Now on equivalence, you absolutely care what the charge is, but on osmolarity, you don't. Plus, we would have 2 moles of chloride particles per liter. And so now we're just going to add that up. Total, the osmolarity would be 3, or it would be 3 osmoles. I hope this is clicking. Feel very blind not having you guys on Zoom to tell me this is not clicking, so I hope it is. All right, what about 3 molar glucose? So we have 3 moles per liter of capital G glucose. That's going to break apart into how many particles? This is a trick question because it doesn't break apart into ions or any smaller particles. It's just going to be glucose. Glucose doesn't dissolve into small, it can dissolve, but it doesn't break apart, it doesn't disassociate, would be the better word. So if we have 3 moles per liter of glucose, we have 3 osmoles. Osmolarity of 3. All right, that one was more simple because it does not disassociate into ions. All right, a very good example with osmosis. I told you this video is going to be a little bit longer. We have 2 more slides and then we're done. I'm not really going to talk about dialysis a whole bunch. We will talk about how osmosis works with oxygen transport, but let's talk about red blood cells and oxygen transport, and then that's it. So red blood cells, we know they look like cushy little donuts, kind of. They're supposed to be kind of plump. These are red blood cells in isotonic solution, meaning that the solution outside of these red blood cells, so the solution all in here, this solution, has an equal number of particles per liter as the solution inside the red blood cell, okay, in here. Equal number of particles. And so because of that, there's no gradient and there's no rush of solvent any direction. Everybody's happy. And the red blood cells look like they should. These are healthy red blood cells. All right. If you look at these red blood cells look kind of swollen. All right. They look a little too plump. Okay. They just got done eating their Thanksgiving lunch. And these are in hypotonic solution. So what that means is that the solution out here has a, right, if they are swelling, these are because it has a, hypotonic means a lower osmolarity, okay? So if we were looking at this red blood cell right here, what happened is that we have a low concentration of particles out here, and we had a very high concentration of particles in here. And because of that, the solvent, remember, it always moves from the gradient here. Solvent always moves from low concentration to high concentration. So we draw a picture of that. All the solvent is going to rush into the blood cell. And that is what causes it to swell. All right? And if it swells too much, it could burst. So that's bad when red blood cells are in hypotonic solution. It's also bad when red blood cells are in hypertonic solution. Okay? This, you might have seen a picture of it, is very similar to, you all have heard of probably sickle cell anemia. These look like anemic blood cells. Okay? They're very shriveled. If I misspelled that, you just know that I'm not good at spelling. They look a little bit shriveled because they're in hypertonic solution, meaning the solution outside of these blood cells has a higher osmolarity than the solution inside the red blood cells. Okay, so what that looks like is we've got a lot of particles in the solution outside the red blood cell. High concentration, and we have a low concentration of particles in the red blood cell. So that causes the solvent to rush out of the blood cell, to just leave it. And then you are left with a shrunken, shriveled red blood cell because the solvent has left. Okay? So if I had you calculate osmolarities and then compare different solutions, I would hope you could tell me if something is isotonic or hypotonic or hypertonic compared to another solution. And we should have some practice problems. If not from the test book, then for sure for review for the exam. But I hope you're taking notes. I hope you ask me your questions either via email or at the beginning of another lecture. We only have a few lectures left, and I'm happy to talk through any of this again. Okay, last topic on osmosis. How does osmosis relate to oxygen transport? Well, this is how oxygen transport happens. So we know that we breathe in oxygen, and that oxygen goes straight to our blood. So we have this highly oxygenated blood, which is represented on the left side of the picture. So we have a high concentration of O2 in the blood, and cells need that, right? So our cells, so this is highly oxygenated blood. And our cells have a low concentration of oxygen, all right? They need oxygen. And so what we see is there's a gradient here. And what cells have a lot of, though, is as they function and as they work and as they make things and take care of business, they create CO2. So they have a high concentration of CO2, and they have a high concentration of waste. Okay, just other things they need to get rid of. So they need oxygen, and they want to get rid of CO2 and waste. Well, we know highly oxygenated blood has a low amount of CO2 and a low concentration of waste. It's freshly oxygenated. So you see there's gradients here that are set up for this exchange. Now here, bear in mind that let's see, I'm reading this stuff in here. Red blood cells, proteins. As blood travels throughout the body, we know that the smallest of smallest veins we call capillaries. And in those capillaries, if you zoom in, you're starting to see these individual red blood cells that have proteins and all kinds of things in them. And this process is showing you here what's happening at the capillaries. This is where the transaction occurs. This is where the cells get the things they need, and they get rid of the things that they don't need. And so because of these concentration gradients, because there's a low concentration of oxygen in the cells, and there's a fresh high concentration of oxygen in the blood, that solvent is going to push the oxygen and the nutrients and those raw materials to the cells, and at the same time those cells are going to, or I should say the CO2 and the waste is going to be drawn out of the cells towards the low concentration, towards the blood where those things are low in concentration. And then from those capillaries, they're going to travel back to our larger veins and eventually back to our lungs, where we will get rid of those things. So again, this is all concentration based. It's all gradient based. And so if I ask you how osmosis works, you would simply tell me or remind me that not how osmosis works. We've talked about that, but how osmosis is related to oxygen transport. You would tell me the gradients, freshly oxygenated blood, you would talk about the high concentrations and low concentrations of the oxygen and the CO2 and those things, and how that relates to the cells, and how that sets up a gradient, and how oxygen moves from an area of high concentration to low concentration in the cells, and how CO2 moves from an area of high concentration from the cells to the blood where it's low in concentration, so that our body can expel it. All right. End note, this is also how dialysis works for people who have kidney failure and need to have dialysis done for them so that it can clean their blood for them. We extract blood out of their body, run it through, it's pumped through these dialysis bags that have semi-permeable membranes. The solution in the dialysis bags is really clean, and so all the waste and things are pulled out of the blood. If we zoomed in here, here's our blood, it's red. We would pull out all the waste and CO2. I didn't leave enough room. I didn't write CO2. Into the dialysis solution, and then our blood is clean and it's filtered back through to the body, and they're constantly changing the solution, keeping it clean so that gradient stays really strong. So sorry about